p less than 0.05. The trouble is it doesn't tell us where that difference is. Is it the first group versus the second group, the first group versus the third group, or the first two groups versus the third group, and so on? We don't actually know where the difference is. So all it tells us in ANOVA is that two or more means differ from each other. So we need to know which particular means are different from which other means. And multiple comparisons allows us to investigate these hypotheses about means. Now there's two types of comparisons. There are planned comparisons. A priori, they are known as, and these are planned before you collect your data. So before you look at your data, or before you've collected your data, you decide that this particular group is of interest compared with another group. Okay? Or there are post hoc comparisons, and these are comparisons which you decide to look at after you've collected your data. So you might do a graph of the means, and you'd see, oh yeah, so the first group and the fifth group, they look really different. Let's check to see if that comes out statistically significant. So this is looking at it post hoc, after you've collected your data. Now this is quite a subjective procedure, and so I'm just going to give you, for the example that I used yesterday, for the Parkinson's patients, we had 4 groups. I'm going to give you, it's kind of subjective, I'm going to suggest some comparisons which are a priori and others that are post hoc, but you may disagree and you can decide other ones, okay? So, as I say, it's subjective. Okay, so I think an important comparison, a priori, before I've got any data at all, would be to know whether our new therapy, the new age therapy, is different from conventional therapy. Is it maybe the same as? We saw it was below, but actually this is a priori, so we haven't looked at any data. A priori, I would be interested in this comparison. Is it the same or better than conventional therapy? If it's worse than conventional therapy, then it wouldn't be worth adopting this treatment. Another one would be, well, new age therapy, is it any different from placebo control? Maybe it's just like a placebo. So that's a second one. And a third one would be, well, how large is the placebo effect? Is there a placebo effect? So this is placebo versus doing nothing at all, the no therapy control. Okay, so those are my a priori comparisons, and actually you can have as many a priori comparisons as you want, but then if you cover all of them, there are 6 possible comparisons here, then people might not believe you and say, well, you're just covering your bases here, you're going to say everything is a priori. Anyway, if some of them are a priori and some of them are post hoc, I will show you the others which would be post hoc. So these are just the remaining comparisons between placebo control and conventional therapy, between no therapy control and conventional, and between no therapy versus new age therapy. So we've got 4 groups, and if we take comparisons 2 at a time, there are 6 such comparisons. If you've got 3 groups, there are only 3 comparisons. So let me just go through those. A versus B, A versus C, and B versus C. Okay, the order doesn't matter. So for 3 comparisons, for 3 groups, there are 3 comparisons. For 4 groups, there are 6 comparisons. And the number increases as you increase the number of groups. Okay, as I say, as you increase the number of groups, 5 groups, you get 10 pairwise comparisons, 6, you get 15. With 15 groups, you get 105 comparisons. Now, it's pretty rare to be having 15 groups analyzed, but 105 comparisons, let us say we had these 15 groups. If the null hypothesis was true, In other words, all my data was just randomly selected from the same population, all 15 groups came from the same population, then how many would you expect of these comparisons to come out statistically significant, less than 0.05, roughly? At least. Any idea? We're working at 5% significance level, we're doing 105 tests. No idea. Okay, I thought we kind of did this before. The data are random. Now, what we'd be doing if the data is random is the null hypothesis is true, all right? And we would be, what's the probability of rejecting the null hypothesis if the data was true in a particular test that is set at 5%, right? So if we do 20 tests, we would expect one of them to be a false positive. So if we do 100 tests or more than 100, we would expect 5 of them to be falsely positive. So this would be making type 1 errors repeatedly, 5 times, probably 5 times or more. Okay, and one of those would probably be significant. Yeah, okay, so 5 would be significant at the 5% level. Okay, so this is the problem that we face when we're doing lots of comparisons or lots of statistical tests on a set of data. We need to control the number of false positives that we get within the family of these comparisons. Here's just a little cartoon for you to look at. Basically, these are about jelly beans and seeing whether they cause acne, particular colors. They test all the different colors. As you know, these little jelly beans, they come in many different colors. They test the first one, which is the purple. No, there's no significant effect there. They try the brown one, no significant effect. The pink one, no. Finally, the green one, they get statistical significance. So it must be the green ones that are linked with acne. Well, because they've tested so many times, 20 times here, if you look at this, yes, it's 20 times, then one of these is likely to be falsely significant. So that's probably what's happened here. Okay, so post hoc tests, how do they arise? Well, sometimes you only think about particular comparisons. If you've got a lot of data, if you're recording lots of variables, you only think about possible correlations or possible differences after you've looked at the data and you've checked it. So you do your little scatter plots of the different variables, or you do a means plot, and you see that certain groups are different or associated with certain other groups. Or the investigator fishes around for significant effects. This is known now as p-hacking. So basically, you just do all the comparisons you can, okay? And there are people that do this. They've got a lot of data, they've got a lot of variables, and basically they just do any test they can think of, and they suddenly find p-values. Of course, they're going to find p-values less than 0.05. This is known as p-hacking, and then they write it up, and they think, post hoc, they think afterwards, why is it that these two variables are correlated, or why is there a difference between these two groups? And any justification can come up and be credible, and then you publish it. Of course, the problem is that this could be a type 1 error, and when people come to replicate, they don't get the same result. And it's thought that a lot of research is non-replicable. In medicine, you'll be depressed to hear that about 50% of results that are published are not replicable. And that's in the best journals, not just the rubbish journals. Okay, so either way, whatever you do, whether you're looking at your data or whether you're doing these kind of p-hacking, you need to use a post hoc test. if you use Fisher's LSD, this stands for least significant difference test. In Jamovi, this is just listed as no correction. It's just like an ordinary t-test, basically. If you've got a priori comparisons, then you can use this for any number of a priori comparisons. So if I had said with our 4 groups that I wanted to do all 6 comparisons a priori, okay, then I could use Fisher's LSD. Okay, it can also be used post hoc testing, but only for comparisons across 3 group means, and this requires initially that the ANOVA comes out statistically significant, and so it's called a protected t-test. This is a good test. Actually, it's the most powerful test, so if you can use it, then you should use it, and you should be thinking about your data before you've collected it. You should be thinking about which comparisons are important. Which hypotheses do you really want to test? So this is a very important part of the research process. You don't just collect loads of data and then try and find statistical significance. That's a very poor way of doing research. Okay, so for post hoc tests, there's Tukey's HSD, wonderfully known honestly significant difference test. And we use this when there are more than 3 conditions. And it compares many means, many pairs of means, while controlling for this family-wise error rate. Apart from Fisher's LSD, the Tukey test is one of the most powerful post-hoc tests. And there is a general procedure known as the Bonferroni test, which is just basically the number of tests that you do, you divide that into the significance level. So if your significance level is 5% and you've got 5 tests, then you divide 5 into 0.005 and you get 0.01, like this. So then that means you need to achieve a p-value of 0.01 or less in order to claim statistical significance at the 5% level. Okay. So I think I could demonstrate this in ANOVA. Right. Let me just see what these two. Yeah. Okay. So yesterday I told you there are 2 ways of doing the one-way ANOVA. You can do it with the one-way ANOVA, or you can do it in the ANOVA. I'll show both of them. I just need to label these. So what is this? Okay. So now if I go to analyses ANOVA and I select ANOVA here, this is the more general procedure which allows me to put in more than one factor. We've only got one factor, and that is the treatment. We've got 4 levels of that factor. Okay. Let's see. So then, in order to get the post hoc tests, you go down to here, click on here, and you need to enter that into here. And Tukey is the default, but you can select the no correction, which is Fisher's LSD, or the Bonferroni that I told you about, or the Sheffe. The Sheffe is the least sensitive test. So you probably want to use a sensitive test. Bonferroni is not very sensitive. The no correction Fisher's test is the most sensitive, but that's only for a priori comparisons. If we're doing post hoc tests, then Tukey is the best test. So let's see if we can move this around a bit. Oops. Okay, so we've got our table, our output here. Yeah, okay, so these are the different comparisons. I think I'm going to have to move, let's see. Okay, for some reason it doesn't want to move. Right, let's go. Ah, I see, okay. Okay, so what we have is the Tukey's p-value here, all right? So you can see that NT versus PC, NT was no treatment versus placebo control was significant, 0.002. NT versus the conventional therapy is significant, P less than 0.001. And NT versus the new H therapy is also highly statistically significant. So basically this tells us that all three other treatments are significantly better than no treatment at all, including placebo. And then you can see here, so we've got PC versus, so this is placebo control versus conventional therapy. That is significant. In other words, conventional therapy is better than a placebo. That's good news. PC versus the new age therapy, you'll see that is not significant here. And the final comparison is conventional therapy versus new age therapy, and that is significant. In other words, new age therapy is significantly worse than conventional therapy. Okay, the other way to do this is to run the one-way ANOVA like this. And again, we just put in the variables and we go down to post hoc tests. So this is what you'll be doing today. You'll be selecting this Tukey, and let's have a look. And it's basically the same as what we saw before. We should get exactly the same results. But the format is slightly different, okay? It's different in that the p-values are given below the mean differences. So you can see here that these mean differences, they're all negative because we're comparing with the no therapy. So it's no therapy, take away these. And so compared with the placebo control, this is the p-value versus conventional. This is the p-value, highly significant. And then, okay, yeah, here we go. And then the placebo control versus conventional therapy, highly significant. The one that is not different is the placebo control and the new age therapy. This is as we saw before, so 0.878. Final one, conventional therapy versus new age therapy is significant. In other words, conventional therapy is significantly greater effect than new age therapy. Okay. So someone's asked a question, I think. Post hoc test is looking for where there is significant results across all the possible comparisons. Essentially, yes. It means that if you're doing a post hoc comparison, then you will be looking at every possible. You could look at every possible comparison. That is correct. If you're doing that, then you need to correct your calculations, which is what Tukey is about. It makes it a bit more difficult to get statistically significant results. Now let me just show that to you in the previous analysis here. If I was to show you the no correction, then if we look at this table that we had before, we've got the p-value here, which is from Fisher's LSD, okay? And you'll see that these p-values are a bit less than the Tukey p-values. All of them are. That's because it's more sensitive, but this is an a priori test only, unless you have three groups and the ANOVA comes out statistically significant beforehand. Someone's asking this project thingy, submission thingy, supposed to do. We're going to be doing that later. Don't worry, don't panic. Okay, so I'll just go back to the presentation and let's see. Okay. Right. So Bonferroni, I've explained. And actually, Bonferroni is a general post hoc procedure, so you can use this for correlations, for chi-squares, for any test at all. So it is quite useful. The trouble is it's a rather blunt instrument. It's not very sensitive. So this was just showing you how it was done. And yeah, I've included the Bonferroni here. So you can see Bonferroni is even larger than the Tukey. It's slightly larger than the Tukey. So it's not such a sensitive test. The error rate is 5%. Yes, that is our significance level. That's what it means. Alpha is our significance level. It's the probability of making a type 1 error. That is what we use when we do statistical tests. Okay. So this first P, this is for Fisher's P, where there's, what was it? No, where there was no correction. That's the same as Fisher's. This is Tukey, this is Bonferroni. Okay, so Fisher's uncorrected. Okay. So we do it in two ways. This is the way you're going to do it today, by the way, in the lab after this lecture. One of the questions that you do will be a one-way ANOVA. And right, so I've actually gone through this, but let me go through it again. These are the highlighted p-values. The red ones are statistically significant. Basically, everything is different from the no treatment group, okay? And the only one that is not significant is between the placebo control and the new age therapy. This does suggest that new age therapy is really a bit like the placebo. So this p-value here, 0.877, is clearly much greater than 0.05. Okay, so how would we summarize these comparisons? And again, this is something you're going to do today, so please look at this slide when you do your comparisons, when you do your summaries. So you just use these p-values, okay? So what we're doing here is comparing the no treatment with placebo control, conventional therapy, and new age therapy. And if you see these 0.002, less than 0.001, and 0.028, these are where these numbers come from. I've worked to 3 decimal places, except for this one where it was very significant, 4 decimal places. Usually 3 decimal places is good enough. Okay, so which test are we going to use? Well, a priori, we should use Fisher's LSD. This is the best test. Post hoc, which we often have to do. As I say, if you've got three conditions or 3 treatments, then use the protected Fisher's LSD. For more than 3 conditions, then use Tukey or Bonferroni. If you've got very many comparisons, let us say more than 6, I would recommend using this Benjamini-Hochberg test, which is quite clever. It's got a false discovery rate procedure. It's actually quite straightforward. You can set it up in an Excel sheet to do it. And if you want to read the paper, if you happen to start to do this sort of multiple comparisons, which is done a lot in genomics research with microarrays and that sort of thing, they're doing not just tens of comparisons, they're doing thousands of comparisons. So that can be quite a useful procedure. Okay, I'm just going to finish. My very last slide is about software packages. Yeah, Minitab is nice to use. A lot of people use this in sciences. Trouble is it's not free. SAS is also menus, nice and easy to use, but not free. SPSS, similar. R is a good package, but the trouble is it's rather difficult to use. It's menu driven, so it's not menu driven. You have to type in commands. So it's like a program. It's really a programming language. Jamovi is a kind of interface with R, and I think is very useful. You can also run R in Jamovi, and it's free. So these two last things I would recommend. Thanks very much, and enjoy your stats wherever you may do them. I think we'll have a break now for, what should we say, 10 minutes, 15 minutes? Maybe till 1:45, all right? And then we'll do the lab. Okay, that should give us enough time. Okay.